Good morning. Myself, Dr. Shubhankar Sen, an associate professor from the Department of Mechanical Engineering, IIT ISM Dhanbad, welcome you to the third lecture of Module 8 of the 12-week SHIAM NPTEL course, Finite Element Method in Thermal Engineering. In today's class, we shall illustrate the Galerkin finite element solution of one-dimensional steady convection diffusion transport equation by using two-noded bar elements. So here we have considered one-dimensional convection diffusion equation and we shall use two-noded bar elements. This is the question that we have to solve the distribution of the degree of freedom U for an one-dimensional problem. So we have the domain, this is x equals to 0 and this is x equals to 1. This is the x direction. Our governing equation is C du dx equals to nu d2u dx2 plus sx. So we shall use GFEM for two-noded bar elements. Our length of this domain, this is L equals to 1 meter. We have been given C is the convective velocity. This is 1 meter per second. And we have to find a solution for different Peclet numbers. We shall consider two Peclet numbers. So we shall solve for P equals to 1 and 5. Our source term value is given as 1 unit and U is the degree of freedom, where U equals to U of x. So we have essential boundary condition at both the ends. So U at x equals to 0 and U at x equals to 1 equals to 0. So if the source term is also 0, it will reduce to an eigenvalue problem. But we have non-homogeneous source term. We have homogeneous EBC at both ends. Since the source term is non-homogeneous, we shall get unique solutions for Ux if the source term Sx equals to 0, the problem reduces to an eigenvalue problem, where we have multiple solutions subject to different eigenvalues. Now we shall discretize the computational domain into 10 elements, 10 two-noded bar elements. So we begin with the pre-processing. Our governing equation is, the strong form is C du dx equals to nu d2u dx2 plus sx over omega. So in preprocessor, let us begin with the mesh generation. Mesh generation, we use 10 two-noded bar elements. This gives us number of elements, num equals to 10, and number of nodal points in the entire mesh, num n p equals to 11. So this is our domain. So we have 11 nodes, 3, 4, 5, 6, 7, 8, 9, 10, 11. So global node 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is the x direction. This is our mesh size. So this is delta x. Delta x equals to 0.1 meter. This is our element 1, element 2, element 3, element 4, element 5, element 6, element 7, element 8, element 9, and finally element 10. So we generate the IEM array here. E is varying from 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Our A is varying from 1 to 2. So we fill the boxes here. For element 1, our global nodes are 1 and 2. For element 2, these are 2 and 3. For element 3, these are 3 and 4. And accordingly, we have 4, 5, 5, 6, 6, 7, 7, 8, 8, 9, 9, 10, 10, and finally 11. Now we generate the ID array. So for ID array, we make the mesh once more. So element 1, element 2, element 3, element 4, element 5, element 6, element 7, element 8, element 9, and finally we shall have here element 10. So here at the left and right boundaries, our degree of freedom values are specified as EBCs. So we shall have 0 equation numbers at global nodes 1 and 11. So here equation number is 0, equation number is 0. So for global nodes 2 to 10, our equation numbers will start from 1 and it will end at equation number 9. So equation number 1, 2, 3, 4, 5, 6, 7, 8, and 9. So here these are our elements and these are our global equation numbers. Now we make the ID array A versus ID A. A is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So here our equation numbers, they will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. We have the ID array ready now, so we can make the final LM array. So here we have the LM array is constructed as, here we have E, A, I, N, E. E is varying from 1 to 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Our local nodes are 1 and 2. Our IDOF is 1. We have one equation per node. So therefore, per element, we have 2 equations at local level. So these equations are coming under the heading of NEE. These are 1 and 2 respectively. So here we have the equation numbers as, for the first element we have 0, 1. Then we have 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, 9, and finally we have 9 and 0. So here we have our sample finite element. This is element E. local node 1 and local node 2. Now we shall have the weak form of the governing equation. We already have derived the weak form and as well as the element level matrix equation for this problem as a generalized unsteady state problem. From there we know that the generalized weak form and matrix equation were already derived in lecture 1 of this module 8. So we shall directly write the governing equation. The element level algebraic equation is given by Cij uj plus Dij uj equals to Fie, or Cij plus Dij uj equals to Fie, or Kij uj equals to Fie, where Kij equals to Cij plus Dij. Now Cij, this is the convection matrix, and Dij, this is the diffusion matrix. So we already know that Cij, this is minus C by 2, C by 2, minus C by 2, C by 2, and Uj, this is U1e, U2e. The diffusion matrix, this is given as C by 2Pex minus C by 2Pex. In the second row we have minus C by 2Pex, and here we have C by 2Pex. Here we have U1e, U2e. The load vector is F1e, F2e. So these derivations are already discussed in lectures 1 and 2 of this module. So we are straight away using the final expressions. So here we can write it as minus C by 2 plus C by 2Pex, C by 2 minus C by 2Pex minus C by 2 minus C by 2Pex, C by 2 plus C by 2Pex. Then we get here the unknown element level load force vector. Then we have the unknown element level degree of freedom vector U1e, U2e equals to F1e, F2e due to source plus F1e, F2e due to the essential boundary condition. Now we can again simplify this expression. So one correction here, this is 0, equation number at the essential boundary node. This is module, the arrow was missing here. This can be written as C by 2 minus 1 plus 1 by Pex Next we have C by 2 into 1 minus 1 by Pex. Here we have C by 2 to minus 1 by Pex, and finally we have C by 2 into 1 plus 1 by Pex. Then the degree of freedom vector is U1e, U2e. The load vector from the source term contribution, we already know that it is S delta x by 2, S delta x by 2 plus F1e, F2e due to the EBC contribution. So here we can perform the assembly process. Now we can perform the assembly of element level matrices and vectors. So we have the LM array. We write it once more. E, A, I, N, E, E, elements 1, 2, 3, 4, 5, 6, 7, 8, 9, local nodes 1 and 2, IDOF 1, 1, number of element equations 1 and 2. Here we have 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, 9, 9, 0 for all the elements. Now we have our element level matrix vector equation system, and then we also have the LM array. We can perform the assembly. Since P equals to Q equals to 9, then we have the maximum 9 equations in the global matrix equation. So the assembled matrix equation system will be of 9 by 9 size, consisting 9 global algebraic equations. So K P Q Q Q equals to FP. This is the global or assembled matrix equation system, where PQ equals to number of global equations. Both of them, they vary from 1 to 9 for the given problem. So for the first row, let us perform the assembly. K11 equals to K221 plus K112. We know the construction of the assembled matrix by using the LM array, so we are using it in a straightforward manner. K221, this is C by 2 into 1 plus 1 by Pex plus K112, this is C by 2 into minus 1 plus 1 by Pex. So it gives us 1 by Pex, 1 by Pex, both will be present 2 times. So this will give us C by 2 into 2 by Pex equals to C by PEX. Then we have K12. K12 equals to K122. K122, this is C by 2 into 1 minus 1 by PEX. Now K13, K14 up to K19, all of them will be 0 because 13, 14, 15, etc. they do not belong to the same elements. So K13 equals to K14 equals to K15 up to K19. This is giving us 0. So in the first equation, we shall have only two terms that are non-zero. It indicates that certainly the assembled matrix is heavily sparse. Now we go for the second row. Then we have K21. K21 will be K212. Obviously, we can write it K212 as C by 2 into minus 1 by PEX. Then we have K22. K22 equals to K222 plus K113. K222, this is C by 2 into 1 plus 1 by PEX plus C by 2 into minus 1 plus 1 by PEX. This gives us the diagonal term is C by PEX. Then we have K23. K23 equals to K123. K123. K123 is C by 2 into 1 minus 1 by PEX. Now K24, K25, K26 up to K29, all of them will be 0. So K24 equals to K25 equals to K26 equals to up to K29, all of them are 0. Now we move to the third row. So we have K31 equals to 0, K32, this is K213. K213 means we are having C by 2 into minus 1 by PEX. Then we have K33. K33 equals to K223, K223 plus K114. K114 equals to C by 2 into 1 plus 1 by PEX plus C by 2 into minus 1 plus 1 by PEX equals to C by PEX. So now we have K34 equals to K124. K124 equals to C by 2 into 1 minus 1 by PEX. K35 equals to K36 equals to up to K39 equals to 0. Now we have the assembled coefficient matrix for the first 3 rows. From this pattern, we see that we have only 3 terms present in all of them. In every row, there are only 3 non-zero terms and remaining terms are 0. These non-zero terms, they are one diagonal term, one super diagonal term and one subdiagonal term. By observing this pattern, we can predict that we are going to get a tridiagonal matrix equation system. Then we can also predict the terms in the main diagonal. The main diagonal term will be C by PEX. Similarly, the super diagonal term, it will be the K12 term equals to C by 2 into 1 minus 1 by PEX, and similarly the subdiagonal terms will be C by 2 into minus 1 by PEX. Therefore, from these 3 rows, of the global K matrix, we observe that the matrix K will be tridiagonal. Its main diagonal terms are C by PEX. Its super diagonal terms are C by 2 into 1 minus 1 by PEX. Its sub-diagonal terms are C by 2 into minus 1 minus 1 by PEX. Therefore, we can construct the 9 by 9 K matrix as K equals to K11, K12, K13 up to K19, K21, K22, K23 up to K29, K31, K32, K33 up to K39, K41, K42, K43 up to K49. Like that we can get K81, K82, K83 up to K89, and finally the last equation we get K91, K92, K93 up to K99. So this is our assembled matrix equation structure 9 by 9 matrix. So we can insert the terms here. So in the first row we are getting C by 2 PEX, then we have C by 2 into 1 minus 1 by PEX. Remaining terms will be all 0 in the first equation. 5th term, 6th term, 7th term, 8th term and 9th term. Then in the second equation we shall have C by 2 into minus 1 minus 1 by PEX. Second term will be C by 2 PEX. In the third term of the second equation we shall get C by 2 into 1 minus 1 by PEX. Then remaining all terms in the second equation, they are zeros. Then we come to the third equation. Then the first term is 0. The second term is C by 2 into minus 1 minus 1 by PEX. The diagonal term is C by 2 PEX. The super diagonal term is C by 2 into 1 minus 1 by PEX. So we shall get remaining terms as 0, 5th term, 6th term, 7th term, 8th term and the 9th term. Last equation where the diagonal term is C by 2 PEX. The last subdiagonal term is C by 2 into minus 1 minus 1 by PEX. So in the 9th equation we have 7 zeros. So 1, 2, 3, 4, 5, 6, 7. So we have constructed our 9 by 9 global matrix, which is a tridiagonal matrix. So these terms, this is our main diagonal, then we have our subdiagonal, and then we have our super diagonal. So we have a tridiagonal matrix that is structurally symmetric but numerically asymmetric. Matrix K is heavily sparse. So we have the sub-diagonal, we have the super diagonal, and then here we have the main diagonal. So now we can put the values of Peclet number and we can get the entries of the coefficient matrix. Here there is no 2 in the diagonal terms. It is simply C by PEX. We have shown it already. Now let us construct the 9 by 1 load vector F. We already have the LM array here, E, A, I, N, E, E, 1, 2, 1, 1, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. Our equation numbers are 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, 9, 9, 0 for the 10th element. So here we fill the boxes. So now the load vector F, this is equals to F1, F2, F3, F4, F5, F6, F7, F8 and finally F9. This comes as F1. F1 equals to F21 plus F12. Now this F1, this is associated with the essential boundary. So we implement the essential boundary condition at the left boundary. This will give us K 211 U11. Then we have F2 2 plus F1 3. Then we have F2 3 plus F1 4. Then we have F2 4 plus F1 5. Then we have F2 5 plus F1 6. Then we have F2 6 plus F1 7. Then we have F2 7 plus F1 8. F2 8 plus F1 9. And finally we have F2 9 plus F1 10 minus K 1 to 10 U2 10. Now we have U1 1 equals to 0 and U2 10 equals to 0. Because of that, the contribution of the essential boundary condition, they will both vanish. There will be both 0 contribution. So here we are left with F21 and F12. In the first case, these values are S delta x by 2 plus S delta x by 2 minus K 211 into 0, S delta x by 2 plus S delta x by 2, S delta x by 2 plus S delta x by 2, S delta x by 2 plus S delta x by 2, S delta x by 2 plus S delta x by 2, S delta x by 2 plus S delta x by 2, S delta x by 2 plus S delta x by 2, S delta x by 2 plus S delta x by 2. So we have written for the 8 entries. The last entry is S delta x by 2 plus S delta x by 2 minus k 1 to 10 into 0. So here we can add up all of these quantities. S delta x by 2 plus s delta x by 2, this gives us s delta x, 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 s delta x. So we have the 9 by 1 load vector after implementation of the essential boundary condition. Now we can write the global matrix equation system in terms of the Pecklet number contribution in the coefficient matrix and the source term contribution in the load vector. The global matrix equation system may now be rewritten as, so we have K PQ UQ equals to F. This gives us, we have C by PEX, C by 2, 1 minus 1 by PEX, then we have 0, 0, 0, 0, 0, 0, 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we have C by 2 minus 1 by PEX, C by PEX, C by 2 into 1 minus 1 by PEX, 0, 0, 0, 0, 0, 0. Then we have third equation, 0, C by 2 into minus 1 by PEX, C by PEX. The fourth term, this will be C by 2 into 1 minus 1 by PEX, then 0, 0, 0, 0, 0. Then in the fourth equation, 0, 0, C by 2 minus 1 by PEX. Then we have C by PEX. Then we have C by 2 into 1 minus 1 by PEX. Then we have remaining 4 terms, 0, 0, 0, 0. Then we go to the fifth equation, 0, 0, 0. We have C by 2 minus 1 by PEX, 1 by PEX, C by 2 into 1 minus 1 by PEX. So remaining 3 terms all are 0. Then we go to the sixth equation, 0, 0, 0, 0. Then we have C by 2 minus 1 by PEX, 1 by PEX, C by 2 into 1 minus 1 by PEX. Then we have 0 and 0. We have written the 6 equations. Now we have the seventh equation, 0, 0, 0, 0, 0. C by 2 into minus 1 by PEX, 1 by PEX, C by 2 into 1 minus 1 by, this is 0. We have the seventh equation. Now the eighth equation is 0, 0, 0, 0, 0, 0. Then we have C by 2 minus 1 by PEX, 1 by PEX, C by 2 into 1 minus 1 by PEX. Then we have the last equation, 0, 0, 0, 0, 0, 0, 0. C by 2 into minus 1 by PEX 1 by PEX. So we have constructed the assembled 9 by 9 matrix equation system. Here we have the main diagonal terms. We are indicating the main diagonal. Then we have the super diagonal terms, and then finally we have the sub diagonal terms at the bottom. So we have sub diagonal, we have super diagonal, and we have here the main diagonal. We write it here as main diagonal. Our load vector, it was F equals to S delta x, 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 S delta x. So we have a 9 by 1 load vector. Our unknowns are here. We have the unknowns U1, U2, U3, U4, U5, U6, U7, U8, U9. Then here we have 0, and here we have 0. So here we have shown all our degrees of freedom. Now we have two different values of the Peclet numbers. This is FP. Here in the diagonal it is C by PEX for all the terms. In the subdiagonal terms, sometimes the brackets are missing. So all the brackets are included now. Now we have S equals to 1, delta x equals to 0.1. So the RHS vector is F transpose equals to 0.1, 0.1, 0.1, 0.1, 0.1, 0.1, 0.1, 0.1, 0.1. We have C equals to 1 meter per second. Let us take PE equals to 5. Therefore, C by PE equals to 1 by 5 equals to 0.2. C by 2 into 1 minus 1 by PE equals to 1 by 2 into 1 minus 1 by 5 equals to half into 4 by 5 equals to 2 by 5 equals to 0.4. So our main diagonal terms are 0.2. The super diagonal terms are 0.4. So this is for main diagonal. This is for super diagonal. Our subdiagonal terms are half of minus 1 by PE equals to half of minus 1 minus 1 by 5 equals to minus of half into 6 by 5 equals to minus 3 by 5 equals to minus 0.6. This is subdiagonal term. So now we have all the numerical values. So we can represent the matrix equation system once more. For PE equals to 5, the matrix equation system looks like zero point 0.2, 0.4, 0, 0, 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Here we have minus 0.6, 0.2, 0.4, 0, 0, 0, 0, 0, 0. Then we have 0, minus 0.6, 0.2, 0.4, 0, 0, 0, 0, 0. We have 0, 0, minus 0.6, 0.2, 0.4, 0, 0, 0, 0. 0, 0, 0, minus 0.6, 0.2, 0.4, 0, 0, 0. 0, 0, 0, 0, minus 0.6, 0.2, 0.4, 0, 0. 0, 0, 0, 0, 0, minus 0.6, 0.2, 0.4, 0. 0, 0, 0, 0, 0, 0, minus 0.6, 0.2, 0.4. 0, 0, 0, 0, 0, 0, 0, minus 0.6, 0.2. So we have constructed the tridiagonal matrix equation system where the coefficient matrix is of 9 by 9 size with 3 diagonals, and we can see that this coefficient matrix, this is structurally symmetric as well as numerically asymmetric. Now we have the degree of freedom vectors. The vectors we have already shown in the previous page. So these are u1, u2, u3, u4, u5, u6, u7, u8 and u9. Then our right hand side load vector, this was 0.1 for every term. So these terms will be 0.1, 0.1, 0.1, 0.1, 0.1, 0.1, 0.1, 0.1, 0.1 and finally 0.1. So this is the load vector F. So here we have shown the tridiagonal matrix equation system once more. So the assembled matrix K is structurally symmetric but numerically asymmetric. This is matrix K, this is the load vector and this is the degree of freedom vector. Our degrees of freedom we can show once more: 0, u1, u2, u3, u4, u5, u6, u7, u8, u9 and 0. So this tridiagonal matrix equation system, it can be conveniently solved by using Thomas algorithm that we have already discussed in module 6. So here we have summarized our solutions. So u1, u2, u3 up to u9, all those values, those have been listed here. In the next slide we have plotted these values. So here we have plotted this u versus x curve, and there we see that this is our u1, this is u2, this is u3, this is u4, this is u5, this is u6, this is u7, this is u8 and then this is u9. Then we see that our solution curve, this is an oscillatory curve. So already we have mentioned that the GFEM solutions will be unstable if the modulus of Peclet number falls outside 1. The GFEM solutions will be unstable or oscillatory if modulus of Self-Peclet number less than equals to 1 if this condition is not satisfied. Since PEX equals to 5 is outside this criterion, we get node-to-node oscillatory solutions. These oscillations are known as spurious or non-physical oscillations or wiggles in CFD terminology. So, if we look at the solutions, then you can understand that we have two sets of solutions. So, here solutions appear as if the solutions are different at odd numbered nodes and even numbered nodes, such as the solution is decoupled between those of even and odd numbered nodes. This phenomenon is known as odd even decoupling of solutions. So, if we have our nodes here, we can identify the nodes as 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Then we see that our solution is distributed between the even numbered nodes and odd numbered nodes. So we see that our solutions at nodes 2, 4, 6, 8 and 10, they are high amplitude solutions, and whereas the solutions at nodes 3, 5, 7 and 9, they are low amplitude solutions. So here we have, this is as if high amplitude solutions, and here we have low amplitude solutions. The first case where I have put tick marks, they correspond to even number nodes. So these are solutions at even numbered nodes. And here in the last we have solutions at odd numbered nodes. So when we violate the Peclet number restriction, we get this kind of non-physical or oscillatory solution. But if we use the Peclet number within this range, then we get a physically reasonable solution. So let us now consider PE equals to 1, which is within the stability range. So our diagonal terms will be C by PE equals to 1 by 1 equals to 1. Our super diagonal terms will be C by 2 into 1 minus 1 by PE equals to C by 2 into 1 minus 1 equals to 0, and our subdiagonal terms will be C by 2 into minus 1 minus 1 by PE equals to 1 by 2 into minus 1 equals to minus 1. Therefore, we get a lower bidiagonal matrix for PE equals to 1. This matrix is obviously structurally asymmetric. The KU equals to F assembled matrix equation system is given by, so in the diagonal we have 1, super diagonal is 0, so remaining 8 terms all will be 0, so 0, 0, 0, 0, 0, 0, 0. So we have constructed the first equation in the coefficient matrix portion. So we have 8 zeros, and then we have the second equation. So we have the subdiagonal term minus 1, 1, 0, 0, 0, 0, 0, 0, 0. We have 0, minus 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, minus 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, minus 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, minus 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, minus 1, 1, 0, 0. Then we have 0, 0, 0, 0, 0, 0, minus 1, 1, 0. The last equation we get now 0, 0, 0, 0, 0, 0, 0, minus 1, 1. So we have constructed the lower triangular matrix or the lower bidiagonal matrix for Peclet number 1. Then we have our degrees of freedom as U1, U2, U3, U4, U5, U6, U7, U8 and U9. Then our degree of freedom vector we have mentioned. Now we have the load vector. This is a function of Peclet number. This load vector remains constant. So this is 0 0.1, 0 0.1, 0 0.1, 0 0.1, 0 0.1, 0 0.1, 0 0.1, 0 0.1, 0 0.1. Now we can see that in the first equation we have one equation and one unknown. So in standard Gauss elimination, after the forward reduction we use back substitution. In this case we can get the solution by forward substitution. We can easily find out U1, U2 up to U9 by forward substitution. Consider the first equation. We have U1 equals to 0.1. Consider the second equation. This gives us minus U1 plus U2 equals to 0.1. Now U1 is 0.1. This gives us U2 equals to 0.1 plus 0.1 equals to 0.2. Now similarly we can calculate from the third equation. Minus U2 plus U3 will be 0.1 and U3 will be U2 plus 0.1. So U3 will be 0.3. Similarly U3 equals to 0.3, U4 equals to 0.4 and so on. Therefore, the solution for Peclet number 1 is non-oscillatory. So I conclude today's class here. We have solved steady convection, diffusion equation by using two-noded or linear bar elements. We have considered two values of Peclet number, PE equals to 1 and 5. For PE equals to 1, the assembled matrix is lower bidiagonal. It is structurally asymmetric. We get physically meaningful solution at PE equals to 1. At PE equals to 5, the assembled matrix is tridiagonal. It is structurally symmetric but numerically asymmetric. The solutions for PE equals to 5 are oscillatory and non-physical. For this class, I suggest the books by Professor T.G.R. Hughes as well as Professors Donia and Huerta. Thank you very much for attending my lecture.